Okay, welcome back to the course of Introduction to Algorithms. So in this week, we'll continue to learn about depth-first search, then we'll talk about the breadth-first search. So let's get started. So from the previous week, you know that depth-first search goes as deep as possible. And if you remember from the previous week's pseudocode of the DFS, it was showed the example of DFS in a recursive way. Actually, you can implement DFS in the two ways. First one is iterative, using for while loops, and second is recursive, using recursion. So in the iterative way, you need to use additional data structure, which is a stack. In the iterative way, you need to actually write more code than if we compare with the recursive way. And also you need to declare additional data structure as a stack, as you can see here. So here in this pseudocode, let's take a look on the pseudocode. So let S be a stack, then we push our starting point, okay, then we mark that our starting point as a visited, then we create while loop and say that this while loop will run while S is not empty. I mean the stack is not empty. Then um, inside of the while loop we take the top element from the stack. We then remove that top element. Then we create another for loop inside of the while loop, and we run all the neighboring, all the adjacent vertices of that vertex V here in the graph G. So if some adjacent vertex of V is not visited, as you can see, we push that element into the stack and then we mark that W as a visited. So as you can see, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 lines of the code. So it means that you need to write more lines of code. So let's take a look on how does the iterative implementation work. Actually, there is no difference, but here is like graphical illustration of the iterative implementation of the DFS. So initially we start with the 0, right? And on the 0 we mark 0 as a visited node, as a visited vertex. Then we put into the stack all the adjacent vertices of the zeros, which is 1, 2, and 3. So here, as you can see, stack are filled with the 1, 2, and 3. Next, we take out our top element from the stack, which is the 1, right? We take out 1 and we mark 1 as a visited. Then we take all the adjacent vertices of 1, which is the 0 and the 2. Actually, as you can see, the 0 is already colored into the black. It means we already explored the 0 itself, that vertex, and all the adjacent vertices of 0. So that's why 0 is colored to the black. It means that we don't need to explore that anymore. So when we take out 1 from the stack and explore all the adjacent elements of the 1, we um, we visit all the adjacent elements of the 1, but here we see that 0 is already visited and 2 is already in our stack, so we don't put anything into the stack. We just take out 1 and that's it. On the next step we take 2 from our stack, because 2 is on the top of our stack. We explore all the adjacent elements, all the adjacent vertices of 2, which is 0 we visited, 1 is visited, and 4 is still not in our stack and it's not visited yet. So we put 4 into our stack, so our top element becomes 4. So if you remember, the stack works as a principle of last in, first out. and we take out 2 from the stack and mark 2 as a visited. Okay. Next, we take out 4 from our stack, but the only adjacent element of the 4 is the 2, but we visited 2 before. That's why we just take out 4 from the stack and mark it as a visited, and the only element that stays on our stack is a 3. We take out 3, and the 3 doesn't have any unvisited adjacent vertices, so we put 3 into the, we mark 3 as a visited and take out 3 from our stack. So in the end our stack is empty. So here is the recursive way of implementation of DFS. If you remember from the iterative way of implementation of DFS, there was 10 lines of the code, and also you needed to create the stack. But here, if you go with the recursive way, there are just only 1, 2, 3, and 4. There are just only 4 ways. There are only 4 lines of the code. So actually, as you may notice, we don't create additional data structure. But when you call recursive, when you implement recursively, the behind the scenes, actually we use a stack, because when we use recursion, that recursion we like store in a memory, and in that memory it's stored as a stack. Even though so we didn't create the stack here, as you can see, the stack is used behind the scenes. So let's take a look at the recursive way. Here we just say that, for example, node or vertex u is visited as a true. Then for each adjacent vertex, if that vertex is not visited, if it is false, then we send the recursion to that node. There are only 4 lines of the code, as you may notice. So next, it's one very big topic. It's about BreadthFirst Search. It's also searching algorithm on finding some elements on a graph. It is very similar to the DFS, but it uses different approach and different technique to find the element. So what is a BreadthFirst Search? BreadthFirst Search is a traversing algorithm where you should start traversing from selected node and traverse the graph layer-wise, exploring the neighbor nodes. You must then move towards the next layer neighbor nodes. BFS is named because it expands the frontier between discovered and undiscovered vertices uniformly across the breadth of the frontier. So algorithm discovers all the vertices at distance k from S before discovering any vertices at distance k plus 1. So if you remember from the BFS tries to get as deep as possible, while BFS tries to get as wide as possible. And when BFS explores the nodes, it explores all the nodes at the same distance k. So when it finishes exploring all the nodes at distance k, it will start to explore all the nodes, all the vertices at distance k plus 1. Then after exploring k plus 1, it will explore all the vertices that are on distance on k plus 2, and etc. till the end of the graph. So let's say that we have graph G with vertices V and edges E, and distinguished source vertex S. BFS systematically explores the edges of G to discover every vertex that is reachable from S. So it also computes the distance from S to each reachable vertex. As a result of the BFS, it produces a breadth-first tree with a root S that contains all the reachable vertices. So even though if we get some graph and if we do some BFS on a tree, on a graph, as a result of that BFS, we can get the breadth-first tree as a result, where S will be the root of the tree. For any vertex reachable from S, the simple path in the breadth-first search tree from S to corresponds to a shortest path from S to in G. That is a path containing all smallest number of edges. The algorithm works both on directed and undirected graphs. So after using the BFS and launching the BFS from some starting vertex S, we will get the result as the shortest path from the S to any other vertices in a graph G. And BFS helps to find the smallest path, the shortest path in terms of the smallest number of edges. And as I said before, the algorithm works for both directed and undirected graphs. So let's take a look at the BFS step by step. How does it work? For this, we in a graph, let's say that we have some graph, and each vertex can be colored into white, gray, or black. If the vertex is white, it means that we didn't start to discover that vertex. Gray means that we are currently discovering the vertex gray, that vertex. And black means that we fully finished discovering that vertex. So all vertices start out as white, then they become gray, and then black. So at the vertex is discovered the first time and it is encountered during the search, at which it becomes non-white. It becomes first gray, then becomes black. So also if some edge UV and vertex U is a black, then vertex V is as a gray or black. Okay, thus all vertices adjacent to black vertices have been discovered. So if we have some vertex U and this vertex has edge UV, it means that our vertex V is either gray or black, right? Because when we discover vertex U, we discover all adjacent vertices of U, and if it has edge UV, it means that V is already gray or black. And but some gray vertices may have some adjacent white vertices. They represent the frontier between discovered and undiscovered vertices. So here is a graph. As you can see, the graph is undirected, and let's say that we have starting point vertex S, and we start to explore this graph. By the way, we use some additional data structure Q and put it into the Q. We put S and we mark 0 because it's our first element. So it's kind of like discovery time is 0. Then we start to explore all the adjacent elements of the S, which is the R and W, right? So we remove this S from our data structure, and we put W and R into our data structure, and we give the discovery time as 1 after 0. Then we take out W, and we start to discover, and as you may notice here, we colored S as a black because it means that we have already discovered totally discovered S, and we then colored R and W into the gray. It means that we still discovering R and W, and it is in our data structure. So we take out W from our data structure and start to explore all the adjacent elements. So it's a T and X. So we take out W from our data structure and put T and X into our data structure, and the first element is R, so we take out R. we put adjacent element of R into our data structure, which is a V, right? So it's a T. After these steps, our data structure becomes T, X, and V, and all the discovery time is equal to 2. Because why 2? Because it takes like predecessor of the element, predecessor of that vertex, and do plus 1. Because as you may notice, T and X, they were discovered after taking W, and W had 1. So we just add one more like time and say it's a 2, and same for the V. Because the predecessor of the V is R, and R has 1, that's why V has 2. On the next step, we take out T, right? And from the T, we start to explore all the adjacent elements that is not in our data structure, but it's not non-discovered yet. And the adjacent element of the T is U, so we put U here, and we give 3 because it's the predecessor is 2, is T, and the T has 2. That's why we add one more, and it is 3. Then on the next step, we take out X, right? X has only undiscovered adjacent element is this Y, right? So we put Y here and give 3 because X has 2. Then on next step, we have only 2 elements that we are discovering. So we take out U, but U doesn't have any undiscovered adjacent elements. So we just take out U, then we have Y. Y has the same condition as it had U, so we take out Y from our data structure, and in the end we don't have any element in our queue, so our queue is empty. So if you remember from the DFS, we used additional data structure, which is a stack. So how do you think, what data structure do we need to use in BFS implementation? The answer is a queue. As you may notice from the previous slides, we use queue, and that data structure worked as a principle of first in, first out. So here is the pseudocode of the BFS. So BFS works as like this. We first initially start to give the color to each vertex as white, right? Then it has property D. It's kind of like discovery time. If you remember, it will every vertex has some number, and that number was like from the previous predecessor plus 1. So this is the D. Initially it's infinity, and the P is the predecessor of that vertex. Then we start to explore from the starting point S. We color that starting point to the gray, then we give D to the 0, then predecessor is nil, because before that we didn't explore any other vertices. We create the queue, right? Then we enqueue into the queue our S, then we run our while loop and say while queue is not empty. Then inside of the while we take out element from the queue and we do dec, so U. Then for each vertex, adjacent vertices of U, we start to explore all the adjacent elements. So if the color is white, so it means we didn't discover it, we color it to the gray. Then we take the predecessor time and do it plus 1. Then we say that predecessor of the V is U, because we take V from the adjacent of the U, right? Then we enqueue that V into our queue. And in the end, after exploring all the adjacent elements of the U, we color U as a black. So this is how does BFS works. Next, it's an analysis of the BFS. So here we talk about the time complexity of the BFS. So after initialization, BFS never widens a vertex, and thus in line 13, ensures that each vertex is enqueued at most once, and hence dequeued at most once. Here, if you notice here, line 13, it says if the color is white, it means that we have never discovered that vertex before, and it allows us not to put one vertex twice into our queue. So, and the operations of enqueuing and dequeuing takes all one time complexity. So the total time devoted to the queue operations is big O of V. V is number of vertices. Because the procedure scans the adjacency list of each vertex only when the vertex is dequeued, it scans each adjacency list at most once. Since the sum of the lengths of all adjacent lists is equal to the big theta of E is number of edges, the total time spent in scanning adjacency lists is takes big O of E. So the total time complexity after this is big O of V plus E, right? Because we spend time on enqueuing, dequeuing, and all the operations related to the queue is big O of V, and scanning all the adjacency list takes big O of E. The total time complexity is big O of V plus E. So BFS runs in a linear time in the size of adjacency list representation of G. So again, one more example of the BFS, but it's more like light version of the BFS. So we start to explore this graph and start with vertex A, okay, and we put A into our queue, and we start to explore all of the adjacent elements of the A, which is B, E, and D. So we put first D, E, and then B. So our queue becomes like this. We remove A from our queue. Then we take out D from our queue. But when we discover the adjacent elements of the D, we see that E is still on. It's already in our queue. And A, we have already discovered A. So we just take out the D. So as you can see here, then we take out E and put all the adjacent elements of the E. All the adjacent elements is E or the D, but we discovered it. A, we discovered it. B, it's on our queue. Then it is C and F. So we put C and F into our queue and take out E from the queue. Then next we have B, right? So when we take out the B, all the adjacent elements of the B is already discovered or in our queue. So we just take out the B from the queue. So next step, we take out C from the queue. From C, B's we discovered, E we discovered, F it's in our queue, and the only element, adjacent element of the C is G, so we put G into our queue, and we take out C from our queue, and we have F and G. So we take out F, right? But F, all the adjacent element doesn't have any neighborings. I mean that is not discovered, so we take out F. Then we take G, and G is still not discovered. And in the end, we'll get this kind of pathway of discovering vertices. So if we start from the A, the D was discovered as adjacent of the A, as you can see, and B also discovered as an adjacent element of the A. E also was discovered as an adjacent element of the A. Then C and F was discovered as the adjacent element of the E, and the G was discovered as the adjacent element of the C. So after coloring like this, it helps us to find which one is the predecessor of which element. So predecessor means that previous element for that vertex. For the B, predecessor is A. For the E, predecessor is A also. For D, also predecessor is A. For the C and F, predecessor is E. And for the G, the predecessor is C. Here is the comparison of the DFS and the BFS. Like what would be the plan of exploring the graph if we use DFS. For example, if our starting point is 0, right? Then we go to the 1, then we go to the 3, then we go to the 2, then after the 2 we need to go to again to the 1, but we discovered 1, so we go back to the 3, and the adjacent element of the 3 is a 4, right? After 4 doesn't have any outgoing edges, so we go back to the 3. 3 doesn't have any other adjacent elements. Then we go back to the 1. 1 doesn't have also unvisited adjacent elements. Then we go back to the 0, and 0 has only unvisited element. Adjacent element is 5. So if we would use DFS, the plan would be first we visit 0, then 1, then 3, then 2, then 4, then 5. Okay. Then if we would use BFS, the plan would be we start with let me take other color. Let's say green. So green is the BFS. So we start with 0, right? Sorry. So we would start from 0, then we would discover all adjacent elements at once. So we put into our queue 1, then 4, then 5, right? Then we would take out the 4 from our queue. We would take out 1 from our queue because we put 1 into the queue first. From the 1, we would put 3 into our queue. We wouldn't put 4 because 4 is already in our queue. Then on the next step, we would take out the 4 from our queue, but 4 doesn't have any outgoing edges. That's why we would just take out 4 from our queue. Then we would take 5 from our queue, and 5 doesn't have also any outgoing edges. So we would just take out 5 from our queue. Then in our queue we would have 3, right? We would explore all adjacent. 4 is already explored. Then we would put 2 into our queue. Then take out 3. Then 2 doesn't have any unvisited, undiscovered vertices. So we would just take out the 2 from our queue, and that's it. So in the end, we would our plan of visiting of the nodes would be first we would visit 0, then we would visit 1, then we would visit 4, then we visit 5, then we would visit 3, then we would visit 2. So this is the comparison of the elements. So if actually it was taught before that BFS finds the shortest path, like shortest path meaning less number of edges. So if we have unweighted graph, which algorithm is better to use to find the shortest path between two vertices and y? Okay, so let's say that we have this kind of undirected graph, and we would need to find what is the shortest path between A and C, right? Let's take a look what would DFS do. So DFS, for example, let's start with the A, then it would go to the B, then it would go to the D, and then in the end it would find the C. And DFS would think that shortest path is like this one. Actually, it's not shortest path, of course. It may go directly to the C, but if you would go uh, by like in alphabetical order, the DFS would find the shortest path in this way. But actually, the shortest path would be this, right? Just with using just only one edge. So what BFS would do? It would start with A, then it would explore B, then it would explore C, and it finds C, and it's already found the shortest path between A and C. So that's why the BFS is better in finding shortest paths in unweighted graph, but not also unweighted graph, but also in undirected and in directed graphs. And the problem of DFS is that DFS tries to go as deep as possible, so it tries to go as far as possible. That's why BFS finds the shortest path. Um, BFS and DFS and BFS, of course, they are um, graph search algorithms. It means that they are applicable to find some elements in the graph, but DFS and BFS can be used not only in the trees, in the graphs, it can be used in the problems where you need to consider many possible ways to find a solution. When there are many options, you can represent each option as a child node and explore it by using DFS and or BFS. So let's say that we have some problem, and at that problem we have like 4 or 5 options to consider, and in order to find solution, we need to consider all the 4 or 5 options. In that case, we could use BFS or DFS, and we can kind of like represent that problem. So again, let's say that we have this problem at some point. At some point, we have option 1, right? Option 2, option 3, and option 4. And each of these options have another options, let's say 5, 6, then 7, let's say, then 8, then 9, and 10. If we have that kind of problem when we need to consider all the options and these options has another options and we need to consider them, we can apply BFS or DFS. And even though that problem maybe wasn't represented as a graph or tree, we can uh, convert that problem into the tree or graph. So more about the problems we will discuss on the practice sessions. So for this lecture, readings only one chapter. It's 22.2, okay, from the book of CLRS. Okay. So today's summary is that we need to use stack to implement DFS if we use iterative way. Okay. If we don't use iterative but we prefer the recursive way to implement DFS, we don't need to use stack, but the stack is used behind the scenes inside of the compiler. Queue is necessary to implement the BFS because the principle of the queue is the first in, first out, and we like kind of put all the nodes into the queue and explore all the adjacent elements one by one. And BFS finds the shortest path with a less number of edges. So this is the main idea. This is the biggest advantage of the BFS if we compare with the DFS. Okay, so that's it, guys. Thank you very much. Thank you for your attention. See you. Bye.